In this question, we're told that a particle is projected from a point O, so the origin, on level horizontal ground with a speed of 45.5 meters per second and an angle beta to the horizontal. We've been told that tan beta equals 12/5. Okay, so I'm just going to quickly get a diagram for this. As usual, I want to be able to annotate freely and to add forces and components as I'd like, and to make sure I've represented all the information from the question in the diagram. Okay, so we're told about this initial projection. The initial projection is in this direction with a magnitude 45.5. Immediately, we can find components. The angle of elevation here is beta. So we're going to get 45.5 cosine beta for the initial horizontal velocity and 45.5 sine beta for the initial vertical velocity. As we continue reading, we're told that the particle is moving freely under gravity, as we would expect, and it reaches the greatest height of h above the ground before it lands on the ground at point P. So let me just add those bits in. So this greatest height is going to be h, so I can just label that here. And it hits the ground at P, so let's just mark off O and P. As usual, anytime we're not told the angle, but we are given a trig expression of the angle, such as tan beta equals 12/5, we want to use that not to solve for beta, but to find exact values for sine beta and cosine beta. So let's just set up a triangle here. Here we have beta, and we know that tan beta is 12/5, which means the opposite should be 12, and the adjacent is 5. So 12 and 5. And if you recognize this triangle, we know the hypotenuse is 13. If you didn't recognize it, that's absolutely fine. You can use Pythagoras to get there. So sine beta equals 12/13. Cosine beta equals 5/13. We're going to make sure we use these anytime sine beta or cosine beta come up in a calculation. Part A asks us to find the flight time of the particle. So looking at the diagram, which shows the flight path of the particle, we're looking at the time it takes for the particle to be at point P. Well, we can use some vertical variables to help us here. When the particle has vertical displacement of 0, that's when it's going to be back on the ground. That's when it's going to be at point P. So let's collect those vertical variables to work with. So we want to set the vertical displacement to 0. Its initial velocity, 45.5 sine beta, but we know that that fraction is 12/13. Well, that gives us 42. So initial vertical velocity of 42. We don't know the final velocity. Our acceleration is g, as usual, and we're looking for the time. This all goes into s equals ut plus half at squared. And as we substitute in, we can actually factorize nicely. Let's take out the t, 42 minus 4.9t. So either t is 0, or, with some rearranging, t is 8.57 seconds. Well, these are the two times when the particle was on the ground. Right at the very beginning when it was projected, and when it impacted the ground at point P. So this is the flight time for the particle. In part B, we're asked to use that information to find the distance OP, so the horizontal distance from O to P, and the value of h. Okay, so two slightly different tasks to do. First, let's work horizontally. So we just want to find the horizontal displacement when the time is 8.75. So we're looking for this displacement. We can go ahead and actually just call it OP. The initial horizontal velocity is 45.5 cosine beta. So that's 45.5 times 5/13, which gives us 17.5. We know that when looking at the horizontal components, the initial and final velocity are the same because there is no acceleration. And we're going to set the time to 8.57. Okay, so the formula to use is always the formula for the horizontal displacement, is u times t. So we want 17.5 multiplied by 8.57. And in the calculator, that gives us 150 meters to 3 significant figures. Okay, let's now find h. To find h, we're going to be working vertically, so we'll collect some vertical variables. And we know that we want the final velocity, the final vertical velocity, to be 0. Okay, so collecting all of these, we're going to call this displacement h. That's what the question's asked for. Initial of 42, final of 0, negative 9.8, and an unknown time. The formula to use here, v squared equals u squared plus 2as. Substituting in and rearranging, we get that h is 42 squared over 19.6, which is 90 meters. This maximum height through its flight path is 90 meters. Okay, and finally in part C, we've been asked to determine the speed of the particle 4 seconds after leaving the origin. To find the speed, we're going to need the velocity vector. We need two components for a vector, both the horizontal and the vertical component of velocity after 4 seconds. We know with the horizontal velocity, it's always the same, so I immediately know that that is 17.5. But we still need to find that vertical component. So let's collect all of our vertical variables. The displacement is unknown. The initial velocity is 42, as we used earlier. We don't know this final velocity, is what we're actually looking for in the question. Acceleration due to gravity, and we're setting the time equal to 4. So we're going to use v equals u plus at. If we substitute those values in, we get a velocity of 2.8. Okay, a couple of things to notice here. It's still positive, so that means this particle is still on the way up. So a positive final velocity here means this particle is on the way up still. Maybe it's somewhere like here. To calculate the speed, I just need to find the magnitude of this velocity vector. Now that I have both of its components, here's the diagram that I can use. Here are the two components we're using. 2.8 that we've just calculated, which is still moving up, and 17.5, which is the constant horizontal velocity. Okay, the magnitude of this vector is going to be the speed. We can find the magnitude by using Pythagoras' theorem. The speed is 17.72 meters per second.